Hello students, today I am going to deliver a lecture on Gauss-Markov theorem. This presentation is designed for the BSc CBCS Statistics Honors student studying linear models at BSc 4th semester under Dibrugarh University. Carl Friedrich Gauss, born on 1777, a German mathematician, generally regarded as one of the greatest mathematicians of all time for his contribution to number theory, geometry, probability theory, astronomy, and so on. Gauss was a calculating prodigy, and he retained the ability to do elaborate calculations in his head most of his life. Andrei Markov was born in Russia in 1856 after 1 year of Gauss' date, and he was a student of Sibayev in St. Petersburg University and a successor of Sibayev in Academy of Sciences in Russia. He had a numerous remarkable contribution to probability theory. The Gauss-Markov theorem was named after Carl Friedrich Gauss and Andrei Markov, although Gauss' work significantly predates Markov's. But while Gauss derived the result under the assumption of independence and normality, Markov reduced the assumptions to the form stated that the ordinary least squares estimator has the lowest sampling variance within the class of linear unbiased estimators if the errors in the linear regression model are uncorrelated and have equal variances and expectation value of 0. In the linear model, which is linear in the parameters y equal to x beta plus epsilon, this is given in matrix form where we assume that expectation y equal to x beta and covariance of y equal to sigma square I is the identity matrix, or expectation epsilon, the error term, equal to 0 for all x, the mean independence, and covariance of epsilon equal to sigma square I, that is homogeneous variance or homoscedasticity. Then the Gauss-Markov theorem states that the estimate of the parameter, that is beta cap, equal to x prime x inverse x prime y. This is the based linear unbiased estimator, blue. The based means minimum variance and linear indicates that the estimators are linear functions of y. An estimator is based in a class if it has smaller variance than other estimators in the same class. Here the data are the y, not the x. We are looking at estimators that are linear functions of y, or beta curl equal to small m plus capital M y, where beta is a k by 1 parameter vector, small m is a k by 1 vector of constants, capital M is a k by n matrix of constants, and the data vector y is n by 1. Here we are restricted to the class of unbiased estimators, and hence we require that expectation beta curl equal to beta for any valid possible value of beta. Now, if beta curl is to be unbiased, then expectation beta curl equal to small m plus capital M expectation y. So this is equal to small m plus m expectation x beta plus epsilon. This is the linear model, which is equal to m plus capital M x beta plus m expectation epsilon. And finally, it will be equal to small m plus m x beta, where the last line follows the mean independence assumption, and to be unbiased for any possible values of beta requires small m equal to 0 and capital Mx equal to Ik, the identity matrix of k by k. The least square estimator satisfies these requirements for unbiasedness, since for beta cap, capital M is equal to x prime x inverse x prime, and then mx will be equal to x prime x inverse x prime x equal to Ik, the identity matrix. Thus, for linear unbiased estimators, requires us to look for estimators of the form beta curl equal to my. For that m, that satisfied mx equal to Ik. Without any loss of generality, we can redefine the M matrix to be of the form x prime x inverse x prime plus C. Here C is some k by n matrix, and using one again, we know that for our estimator to be unbiased, which requires that mx equal to ik. So this will be equal to x prime x inverse x prime plus C into x equal to ik, and finally we have ik plus cx equal to ik and cx equal to 0. That is, cx is a k by k matrix of zeros. Now, to compute the covariance matrix of all alternative estimator beta curl, we can write beta curl equal to my. Y is the linear model, x beta plus epsilon. So it will be equal to beta plus m epsilon. And thus we get beta curl minus beta equal to m epsilon. Since it is unbiased by construction, expectation beta curl minus beta will be equal to 0. So that the covariance matrix of the estimator is expectation beta curl minus beta into beta curl minus beta prime, which will be equal to expectation m epsilon prime, and finally we get sigma square m prime, which is a k by k matrix. Now m prime will be equal to x prime x inverse x prime plus C into x prime x inverse into x prime plus C whole thing prime, and this term will be equal to like this: x prime x inverse x prime x inverse plus x prime x inverse x prime C prime plus cx x prime x inverse plus C prime. And we know that cx equal to 0 and as well as x prime C prime equal to 0. So m prime will reduces to x prime x inverse plus C prime. Now the matrix C prime is a k by k cross product matrix, which by construction cannot be negative definite. The best estimator in a class of estimators is the one with the smallest covariance matrix, where small means the covariance matrix associated with any other estimator in the class, that is linear and unbiased, minus the covariance matrix of the best estimator is a positive definite matrix. So the difference m prime minus covariance of the best estimator will be positive definite. Since m prime is minimized when we set the matrix C equal to 0, the best estimator in the class beta cap. Any other estimator m in this class has a strictly larger covariance matrix. Thus, it is concluded that the OLS estimator beta cap is blue under the two conditions set forth, that is mean independence and homoscedasticity. So dear students, I conclude today's lecture here. Thank you.